Hello, let's discuss now about heat pump. So, if I have a gas in a cylinder, and this is the piston, and I push the piston inward, volume decrease, pressure increase, and the temperature also increase. If I do that very fast, I can consider the process almost with no heat exchange with exterior. So if I do the opposite, if I take the piston in that direction, volume increase, pressure decrease, and the temperature decrease of gas. So this is my house. This is interior, let's say outer space. Okay, I have here gas that is very cold. In that situation, the gas, let's say, has 0 degree Celsius, take heat, let's say low heat, and increase temperature to the 5 degree Celsius. Okay, now I compress the gas and I put inward. I go in that direction. 1 second. So increase in temperature, increasing in temperature during this in a process almost with no heat exchange, let's say. So in that situation I have, let's say, 25 room temperature degrees Celsius, and decreasing must decrease to the 1 second 20 degrees Celsius to put the heat high, let's say, in the room. Okay, but it's difficult to have a cylinder with a piston to take it from outside and put it in inside and so on. So it's easy to do so, to have something like this, let's say I have here the compressor, and here we have expansion valves. Okay, so let's say the direction for the gas is this. As you observe, here is expansion, here is compress. So, as you see, we have here high pressure, and here we have low pressure. That means here we have high temperature, and here we have low temperature. Okay, because the difference in that pressure. Okay, so here expansion of gas, we have an almost adiabatically process. Here we have almost adiabatically process, but here we have from let's say 25 degree Celsius to 20 degree Celsius. Just in that condition they can put heat out. It's not possible to extract heat without variation of this temperature. So they say we can approximate this with, just 1 second, this cycle. But this cycle in P and V is something like this, but here is high temperature constant, here is 0, here is that is 0. But as you see, is not constant in temperature, is not constant in temperature, cannot be constant. This and this here, high temperature, is not constant. But there is one more thing here. We have here some amount of heat, high. We have here some amount of heat, let's say low. But they say, they wrote that work done in this cycle is so heat high minus heat low. But as you see, they wrote efficiency is equal work done divided by heat high. Okay, so efficiency in that case will be 1 minus heat cold divided by heat high. I wrote heat low here. Okay, and is 1 minus temperature low divided temperature high. In other words, they wrote, 1 second, efficiency equal work done divided by heat high equal heat high minus heat low divided by heat high. Okay, but for the heat pump, coefficient of performance they said is heat high divided by work done. So is high heat high divided by heat high minus heat low. But you see, what's happened in this case if heat high is almost equal with heat low, but heat high is greater than heat heat low. So this is almost 0 but greater than 0. So this is almost very high value. So can be coefficient of performance very high value? I said no. And let me explain. They said that work done equal heat high minus heat low. Okay, so coefficient of performance must be somehow 1 divided by efficiency. But you see, this okay, I will explain in a second. This is my house. And I have heat pump. I take the same amount of heat and I put it in my house. So the heat, one second, heat high is equal with heat low, is the same amount of heat. So in that situation, this is 0. So the work done is 0. So have no sense, not make sense, this. Okay, so in my point of view, that is in PV diagram similar with Otto cycle. But here is 1, here is 2, here is 3, here is 4. But let's see, is the same. In Otto cycle is the same efficiency, is heat high minus heat low divided by heat high. So here is heat high and here is heat low. One second. Heat low. Okay, so this will be the same 0. Why 0? I will say again, if I have a house, I have a room, I take the same amount of heat from exterior and put it into interior, is the same. And I do that through a heat pump. So, in that situation, what's the coefficient of performance? I let for you that question. Let's answer. So, I said that, in my point of view, the heat pump in PV diagram, Clapeyron diagram, is something like that. Very similar with Otto cycle. Here I have in from outside Q, from exterior, and here we have heat from to interior, the same amount of heat interior. Let's say here is 1, but increase in temperature to 2, 1, that's mean I said 0 degrees, 2, that's mean I said 5 degrees Celsius. Here and here is no exchange of heat. Here there is compressor. but there is mechanical work here. Compressor do a mechanical work, and here we must to be another mechanical work instead of evaporator. So here I have let's say second 25 degrees Celsius. Here we have 20 degrees Celsius. Okay, so this is a cycle, and from my point of view, let's say 1, 2, coefficient of performance is equal work done divide no sorry is heat in the room divided by work done. Okay, so let's see. For a constant volume, 1, 2, 2, volume was constant, but they absorb heat. Okay. In that situation, 1 second. We know that U is amount of gas, the heat for constant volume, and the temperature. If we apply this operator, this is the amount of gas, constant volume heat, and the difference in temperature. And we know that from first law that is heat minus work. What means heat minus work? Let's say we have a steam engine train. Let's say this is a steam engine train. No. Okay, so they have an internal energy that is Joule. So I have here fire that give heat, and the energy increasing with heat and decreasing with mechanical work, but work that the system can make. So in my case, work 1 second. This is this minus this, but I know this is 0 from the compression stage. Okay, so in that case you see this is minus work. This is from exterior. So I give mechanical work to gas. So there is minus amount of gas, heat, specific heat for constant volume, and final temperature minus initial temperature. Okay, so in that situation, this is for the 2, 3, let's say. But the heat for process 1, 2, let's say, equal the same amount of gas, specific heat for volume, for constant volume, and the same final, sorry, minus initial. Okay, let's say here is as point initial is 1, final is 2, initial is 2, final is 3. Okay, let's take an example. In our case, we can write work done is no, 25 minus initial 5 and heat, because here must be a result in Kelvin, and heat is this. We have final 5 minus 0, the same in Kelvin. Okay, so what we can see here, that difference in one way and in other appear to be constant. Here there is 1, 2, here is heat from exterior, and from interior let's say 3, 4, is from the final value minus initial value. As you observe, this is with plus, this is with minus. That means if I give to the system hot, 1 second, I'll show you in a second. Let's say he's a heat pump. This is anyway, can have any shape. So if I if I put the system heat, this is plus. If I take out heat from the system, this is minus. So this is that case, minus, because I take out that heat. But what we can say about mechanical work will be the same. Okay, so in my point of view, coefficient of performance will be obviously heat divided by mechanical work, but you see here what I observe. We have in the cycle, one second, mechanical works here. There is, here is 4, mechanical work for 1, here is another mechanical work 2, 3. Two kind of mechanical work, and we observe the sign of this. Let's see. So I have the convention. If I give to the system mechanical give heat, there is positive heat. I heat up, let's say. Let's say I do the opposite here, but if I do to the system mechanical work, there is with minus. If the system gives me mechanical work, one second. If the system gives me mechanical work, this is a plus mechanical work. Okay, so let's see. Let's remember this. And let's see what's happened. So, heat to the system is, let's say, that heat 1, 2 equal constant value. I said in that example from 0 to 5, the final is 5, but in minus 0 there is Kelvin is equal degrees Celsius plus 273.1, right? The same, this is 3, or there is as you observe, this is plus, this is minus, but doesn't care, we take just one of that, heat that the pump put in my room, And mechanical work. Mechanical work is so from 1 to 2 there is amount of gas, specific heat, and 25 minus 5, this is plus, and mechanical work here, there is 0 minus 20, that is minus. Okay, this is plus, this is minus. This is a problem with this sign, but you easily observe in that case, put to a system, it's a little bit conflicting apparently, to the system. So this is compressor. Okay, but this what's the conclusion? This is heat pump. This is compressed. But here, can I obtain mechanical work? Can I do the expansion, the evaporator, in some manner to obtain useful work? Okay, that's all. I wait for your suggestion, for your I don't know, for your answers.